Okay, welcome back to the shop. So today, we're going to take a look at a three-phase motor starter and some of what goes into using these. It's not overly complicated, though Square D unfortunately didn't make it overly simple. But overall, the biggest thing you have to worry about is the part here that's missing, which is known as a thermal overload, or I think Square D calls them thermal units. So what happens here is this mechanism, this is a regular contactor, basically. We call it a motor starter, but the part that makes it the motor starter is the overload assembly. You can see how that's screwed on there. And this is the overload assembly. And what this is all three phases go through here, and these tabs close this neutral here. So we would land our neutral wire on here, and this here closes the neutral in the circuit going to the contactor. That's this wire here. And that's what allows this contactor to stay in. If this were to open up like they are right now, because there's no overloads in there, this contactor will not close because we've landed the neutral wire here, and if the contactor can't close, the motor can't run. So we've effectively protected our motor. So what goes into all this is you need to have some information from your motor. Knowing the service factor of the motor is handy, and here we can see on our motor our service factor is 1.15. so we can see, if we look at that, try and get this in here, these for Square D, mind you, this is just for Square D sizing, for service factor of 1.15, you can use 100% of their thermal units. And what that's saying is I don't have to add 1.25 to the ampacity rating of the motor in order to size this. They've already figured all that in. Because generally you'll want to size the overloads of a motor at 125% or 1.25 of the full load current of that motor, because that is safety margins, stuff like that. So now that we figured that out, we knew that, the next thing we needed to do was I needed to look up this part of my my starter. So I have a NEMA size 00 starter. It's a class 8536 and it's a series B. So I need to figure out which table, because Square D has like 150 some tables for sizing heaters, which, trust me, will drive you batty. But I did find this paperwork then, and what we have here is class. And here's my 8536, my type, which is SA, which I didn't point out before. I have an SA G12. There we go. The series A and B, so they use the similar heaters there, and my NEMA size 00. So that means, whoops, there we go. Size 00, series AB, and that means I use thermal units table 13. Following with? Yeah, I know, cross-eyed already, but we're getting there. So now we can get to table 13, and what's all this mean? Well, this is all of your current capacities. So 1 TU, 2 TU, 3 TU. One thermal unit would be like if it's a 120 volt motor, you would only have one current carrying conductor. largely. I know there's a neutral, but we don't always do that. So you can just switch the hot. That would be one thermal unit. Two thermal units would be like a 240 volt single phase motor. You would do that with two thermal units, and that would be your ampacity ranges for that. And then three thermal units would be like this, the 3-pole 3-phase starter. And this is our current range as seen on our motor. If we look at our motor, we'll see 200 to 230 volt has 3.2 amps of current. That's full load current in both. The 460 volt here would be 1.6 amps, but we're going with 3.2. So it wouldn't matter in this instance because we're 3.2 amps. It wouldn't matter if we screwed up this 1 TU, 2 TU, 3 TU, 3.2 falls. We're getting this size anyway. So that's a B485 thermal unit. What's that mean? It means you order one of these. And that here is a B485 thermal unit. So now, what's a thermal unit? Well, a thermal unit is actually a pretty interesting little piece of engineering. It's this here goes, we'll bolt in here like this underneath these screws, and the current from the motor flows through here. This here is under spring tension, as you can see, and that spring tension, because it's pushed in as well and under spring tension, so it wants to lift up. So that spring tension is bared down on this gear looking piece, and that can rotate in a little cylinder here, but I can't turn it right now by hand. What allows it to turn is actually there's a alloy of solder in this little cylinder that is calculated out to melt at in this current range that we just figured out here in table 13 for this one. So this solder should melt between 3.00 and 3.42 amps is what would make this solder start to melt, and that once it's melted will allow this to turn, which would allow this reset to pop out, opening the neutral and opening up the contactor altogether. So give us a second here and we'll get all three of these in, and then we'll take a look at resetting this, and we'll talk about some of what can happen when you have these sized wrong, and maybe we'll talk a little bit about the contactors overall. So give us a minute, we'll be back. Okay, so I thought I'd come back quick here and point out something that here we have just one installed, and I have my meter set to continuity here. We have continuity across the thermal overload, and what I don't have though here is our neutral is open. I think we can see that. Yep, there we go. And what I'll do is I'll reset this one tang here. You can see there's just the one here. I'll push the reset down. Now you can see this one didn't come back up. In fact, I can trip it. You can see it came back up there. Reset it. It's down. But I still don't have the neutral, because this is an instance where we've lost two of our phases because there's two not installed. Let me install one more and we'll see what we get. Okay, so we're back now. We got the second one installed. Meter's still working in continuity. We have continuity through these two overloads. Nothing on our neutral yet. Now I have two of these reset. and I still do not have continuity on my neutral. So let's get the third one installed. So when you install these, you want to just make sure that you have the tangs out of the way and that it's sitting in there just right. Get our screws in. Okay, so we're back here and still open. Got continuity, continuity, continuity. Let's reset that, and there we go. We got continuity. So what that's telling us is that you can trip any one of these, and you can see the little yellow trip guy when I did that is out of the way. You don't see the yellow prominently there. If I trip one of these, you got a little trip indicator there. So what happens if any one of these were to trip? We open the neutral. So what that's telling us is these tabs here operate a contact, and each one of these contacts is in series. So we're protecting that motor, that if any one of these phases were to overheat for any reason, whether the motor's bearings are getting worn out and it's resulting in a high current situation for the motor, this will trip. Whether you put a higher load on the motor than it's designed to handle, this will trip. So it's all based on thermal capacity, which is heat, because current creates the heat flowing through here, which is why a lot of guys will call them thermals, or I should say heaters. And that's thermal overloads, heaters. It appears as though Square D calls them thermal units. I don't think I knew that until I started looking this one up. But that's kind of what... This is the protection for your motor. And if this isn't set up right, if you go too high on this, you run the risk of burning up a motor, which can happen. If this is set too low, you can have what they call nuisance trips, because this is still heating up. It does not know what's hooked to it. It's up to you to reference these charts and see that you have it right. A lot of times these things come in an enclosure, and they will have the correct table for them as a sticker in the enclosure, which makes it a lot easier. But when you're trying to find your particular contactor and your and everything else, and what series starter and everything else for the overloads, it can be frustrating. So at least in this instance. Alright, so I thought I'd take a quicker look here at what's actually happening with the neutral. I know I kind of glossed over that. We showed that all three overloads need to be in order for the neutral to properly operate and get the contactor to close. But I thought I'd try and show a little bit more on an electrical diagram exactly what's happening here. So we have L1, L2, and L3 are thermal overloads, and T1, T2, and T3. And what I tried to show here is auxiliary contacts on each one. And what those are is the mechanical system that has the spring finger on it. So what happens here is this is actually, I guess what we would call this is a electrically operated mechanical mechanism. What I'm trying to say in that is that the heat from current flowing through this thermal overload will eventually, as the current goes up, will create more heat, create the solder in that calculated value to become liquid, and the spring tension on this mechanical paw, which is sitting on this cogged overload, will be stronger than the liquid solder, because right now the solder in a cool state is solid, but as we heat up through current, we make the solder liquid, and that opens. Once the solder is liquid, the spring tension is stronger, and it will open this contact. And once we get that contact open, we can no longer have power come in. Here's our feeding neutral for our contactor. It comes up through overload 1's mechanism, and up through overload 2's mechanism, and through overload 3's, except we've had a fault on overload 3, and it has opened. So the current for the neutral going to the coil of the contactor cannot pass through current or the mechanism from overload 3 and complete our circuit. So this being open would then open the coil on our contactor, and hopefully saving our motor from any damage. Hopefully that made sense. This is what they call a series circuit, and that just means that we go through one contact, through another, and through a third, so that if any one of these were to open, we would lose our overall power. It's seriesed up. Some people may recognize that sort of arrangement from Christmas lights, or if you guys are in the trades more, it's much like a stop circuit for 3-wire control or something like that. We always put the stops in series with each other and the starts in parallel. Well, we wouldn't want to put these in parallel, because any one of them could close and close our neutral, and that wouldn't be the desired effect that we're going for here. We need any one of them to open up our contactor and save our motor. So there we go, just a look at motor starter and how they work. This is a simple contactor style, 2 wires, 120 volt coil, so we put 120 volt across this. The contactor itself, the electromagnet in here, will close, and that means that it is one action just down, and there are 3 poles. So it's a single throw triple pole contactor, and this particular one does have an auxiliary contact on it, and that's where they have their relay coil wire going to. So a lot of times you'll put what they call a holding contact on these, and what that is you'll energize this wire once, and it'll hold once it's closed. It's a relay logic thing that maybe we'll get into that. So there we go. Quick little look at a contactor. Hopefully it's interesting. Hopefully it wasn't overly boring, but just something we're messing around with here in the shop. Thought we'd shoot a video. Thanks for watching. Have a great day.